Hello and welcome to this section of the Differential Equations tutor. This section we're going to conclude our problems with constant coefficients and homogeneous equations. These problems we're going to do here are going to be exactly like what we did before, except we'll have initial conditions. So we'll have to do everything we did before to find the general solution, but then we will have to use the initial conditions to go back and find what those constants really are equal to, which will comprise the true solution in terms of the general solution with the initial conditions present. So it'll apply to our particular case of our starting conditions. Right? So what we're going to do is start off with an easier one, just to kind of show you the process. But basically you kind of know how to do this already because you found solutions with initial conditions before. Second derivative of x of t minus 4 times x is equal to 0. So this is our differential equation. We notice it's homogeneous. We know we have constant coefficients and it's linear, so we're go ahead and use our solution technique. So first, let's go ahead and write it in operator notation. D squared minus 4 operating on x of t is equal to 0. Right? So we've done that several times. Now let's go ahead and take this guy and construct our characteristic polynomial. R squared is minus 4 is equal to 0. And one thing that I haven't even told you yet here is our initial conditions are as follows. X of 0 is equal to x prime of 0 is equal to 4. So what this means is that the starting position is equal to 4 and the starting first derivative evaluated at the same time is also equal to 4. So they're both equal to the same number, the function itself and its first derivative. So if this were a position and a velocity, the position would be at 4 meters, the initial velocity would be 4 meters per second if it were representing that. So what we do next is we say, okay, we've got our characteristic polynomial set. This is very easy to solve. R squared is equal to 4. So r is equal to plus or minus 2. Right? Those are our roots. And we've done this enough so we know that when we have roots like this, then the solution, the general solution is x of t is equal to c1 e to the 2t plus c2 e to the negative 2t. We don't have any multiplicity anywhere, right? Because these are totally different numbers, so we just construct it just like this. Now, if we didn't have any initial conditions, we would circle this problem and it would be done. But we need to find these constants, right? So anytime you want to do that, we've done this many times before, you have to use your initial conditions. So one initial condition is we know that at time 0, the position, or x of t, is equal to 4. So we can plug that in and get that guy. So let's go ahead and do that right now. Let's say at time 0, x of t is equal to 4. So we'll have c1 e to the 0 plus c2 e to the 0. The reason I'm putting zeros up here is because it's at time 0. Time is 0 here, time is 0 here. The constants just sit out in front. We're saying it's equal to 4. So what we're really saying is that 4 is equal to c1 plus c2. This is one equation that involves our constants here. I'll put a little star by that. But it's obviously not enough because we have two constants and only one little equation here. So what we need to do is use this to find the first derivative. We need to take the first derivative of our answer so that we can use our other initial condition. The first derivative, x prime of t, just taking the derivative of this guy, is c1 times 2e to the 2t. When you think about it, this is the chain rule. c1 e to the 2t times the derivative of the exponent, which is just 2.